Good morning, everybody. Welcome to my lab report for Lab 6, which is the application of Faraday's law. And in this section of the lab, we're required to collect the observational data of a magnet falling through a conductive tube of aluminum foil, which is a aluminum foil wrapped around a pipe. And then we model the magnet using the VPython code, and we compare our computational results with our observed data. The formulas we use in the lab are shown as above, and we simplify them as the final thing. And because the pipe can be seen as hundreds, like infinitely thin rings piled up together, we'll use the magnetic field for ring formula here. Yep, and the setup of the experiment is very simple. It's just we vertically put the foils, and then we drop the magnet through it, and we measure the time it falls through. And in order to computationally model this progress, we use the following code. So first we create the aluminum tube rings as shown below. This is the section pre-given. And then we calculate the dipole of the bar magnet. And then we calculate the flux, the change of flux due to through each ring that make up the whole pipe due to the magnet. And finally, we let the magnet continue as it goes through the pipe, and we update the velocity, the force on it, and the position of it, and its interaction with the rings, the foils. And then finally, we obtain the result of the beginning time and the ending time, the difference between these two time slots, and we obtain the procedure time of its falling through. Yeah, and this is what the model shows. So first we create the tube, and then this magnet falls through it, and this is in the middle of the tube, and then finally it goes through the tube and falls over. And we find that the predicted time is about 3.12 seconds. And through the data collection using the setup, as I mentioned, we found that the actual time taken is around 3.5 seconds. And the error we predict that is mainly coming from the rotation of magnet in the pipe. So actually, when the magnet is falling down, it's not vertically going down. It's kind of tilted to one side. And sometimes the magnet will rotate in the pipe, causing more resistance and more unpredictable results. So that's why there could be an error. And then there could be measurement error due to our timer used by hand. And also there could be friction between the inner side and the magnets. That will also cause the actual result to be a little bit slower than what we predicted. And now let's come to the what if part. So what if the resistivity of the conductor were reduced to nearly zero? So as the resistivity goes to zero, the magnet will experience stronger electromagnetic braking, which will be caused by the induced current in each rings that make up the pipe. So that's so it will feel a larger braking force that resists it from falling. So it might even stay in the midair, in the middle of the tube. What if the holes and slots are cut into the tube? So if there are holes that disrupt the completeness of the pipe, then it will also disrupt the completeness of the rings, the infinitely thin rings that make up the pipe. So that will cause a smaller induced current and a smaller braking force. So the magnet will fall more rapidly, and it will just feel less braking force and gain a larger velocity due to the gravitational acceleration. And the conclusion is that the experiment is overall successful because we are obtaining the same result as the computational model, but there are still some small errors that might need better instruments and equipment to measure in the standard condition. Yeah, that's all I want to say. Thank you for listening.